Alright, in this video I'm going to re-go over the Nernst equation with you and show you two different ways to do it. The first way is the freshman way, and over here we have the Nernst equation, E equal E naught minus 0.05916 times the log of the reaction quotient, Q, which remember is exactly the same as equilibrium, only it's not at equilibrium. I have outlined right here our Nernst equation, or our cell. In the anode on the left, I have magnesium going to magnesium plus 2, which has a concentration of 1 times 10 to the minus 5th. Over here in the cathode, I have chlorine gas going to chlorine minus at 0.1 with a platinum inert electrode. Notice the bar right here that separates the phases on all these, and this is a salt bridge. Okay, so my half reactions are written down here below. I have magnesium going to magnesium plus 2. Here's E naught for that half reaction, negative 2.306 volts, and that's the anode. I've got chlorine gas going to chloride. E naught is 1.458 volts, and that's the cathode. And this should be very familiar. You probably don't even have to take notes. And here's my balanced reactions with the electrons gone because they canceled when I added them. And that's one thing you won't have to worry about in the other method. My E naught of the cell, E naught of the cathode minus E naught of the anode. Remember, up here, this E naught is a reduction potential. I did not switch it because it was undergoing oxidation. I leave it alone. And I do E of the cathode minus E of the anode, which the book uses E naught plus minus E naught negative to get it. And we get an answer down here of 3.764 volts for E naught. I'll write it in here. All right, moving right along. Here's our Nernst equation. E of the cell equal E naught of the cell minus 0.05916 log of Q. Here's our equation for Q. E of the cell equal E naught of the cell down here minus 0.05916 over n log of the magnesium plus 2 times the chloride concentration squared, because there's a 2 in our balanced reaction up here in the chloride in our reaction, divided by the pressure of chloride divided by the magnesium concentration, or activity, I should say activity, which is 1 because it's a pure solid. We plug those numbers in and we get a final answer of 3.960 volts for this potential. Very high potential. This reaction's going, equilibrium's probably 10 to the 100th. Alright. Now, that's the method you know from freshman chemistry. The second method is to divide the cells. So I'm just going to do, this is method 2 now, I'm just going to do the magnesium by itself and the chloride by itself. And what I'm eventually going to do, I'll write it up here on the right, is I'm going to do E of the cell equal E of the half cell cathode minus E of the 1/2 cell anode. You'll see what I mean in a few minutes. Okay, so up there on the right's what I'm going to do, and that's what I'm doing down here. Alright, so the first thing I did, make sure you write down that 3.960 volts. The first thing I did was I set up my magnesium. Notice it's written it as a reduction. I know it's undergoing oxidation, but when you do it this half cell method, you got to do it as a reduction. Everything's reduction. E naught is negative 2.360 volts, and I set up my equation. E of the half cell, the magnesium half cell, is E naught of the magnesium half cell minus 0.05916 log of Q, which is negative 2.306 volts. That's the E naught of the magnesium right here. Minus 0.05916 divided by 2 electrons times the log of the concentration of magnesium, the activity of magnesium, which is 1 divided by 1 times 10 to the minus 5th. This is upside down from before, but that's because we've written our reaction over on the left here, where I'm circling, as a reduction. This gives us a final answer of negative 2.4539 volts. Now, what I'd like you to do is try to do the E naught of the chloride. I'm going to pause it right here and do that. Meanwhile, I'll write that in right now. Okay, hopefully you've done that by now. I have my cathode reaction written down here. Chlorine plus 2 electrons gives us chloride. E naught is 1.458 volts, and this is the cathode. So my half reaction, half cell potential is E naught of that half cell minus 0.05916 divided by N times the log of Q, which is 1.458 volt minus 0.0596 divided by 2 times the log of 0.1 squared divided by 0.43. That's what you should have written down. Your answer, if you were careful, is 1.506 volts. Okay? And so now the last step to this method is to do E of the cell is equal to E of the half cell for the the chloride, the cathode, minus E of the anode. Let's just write it that way. E of the cathode minus E of the anode. I don't have my naughts in there because they're not naughts. So E of the cathode is the chlorine, which is 1.506 volts, minus E of the anode, which is a negative 2.4539 volts. And when I sum those up, I get 3.960 volts, exactly what we got before. E of my cell equal 3.96 volts right here. I'm going to circle it, start, yee, explosions, fireworks, and that is the same as I got up here, 3.960 volts, explosion, fireworks. It worked. This is nice because you never have to worry about the electrons transfer. Just use the electrons in the half cell. If these, I should have done different ones. If this was 1 electron, I would only put 1 here. I don't have to do 2. I don't have to balance the electrons that way. I just use the electrons that are given in the half cell, and the reaction as written is what you do the Nernst equation for here. And the reaction as written here is what I did the Nernst equation here, and then I just subtract when I'm done. So give that a try. You're welcome to use either method on an exam.